Okay. Since we're talking about multiplying and dividing with integers, what we're really talking about with integers is positive and negative numbers. And we're pretty much comfortable with the idea that a positive times a positive is a positive. And we're probably pretty comfortable with the idea that a positive times a negative is a negative, but you may not have ever really thought about why. And I just kind of want to show you a couple of ways that you could convince yourself or your students that a positive times a negative is a negative. The first way is if we look at multiplication as repeated addition. So let's say we wanted to do 5 times negative 3. Well, we've kind of set up multiplication is repeated addition. If I wanted 5 times negative 3, what I could do instead of that is just say, well, that's negative 3 plus negative 3 plus negative 3 plus negative 3 plus negative 3. That would mean the same thing as 5 times negative 3. And if I were to add those together, you could use a number line, or if your students are really comfortable and they're past that, negative 3 plus negative 3 plus negative 3 plus negative 3 plus negative 3, we're moving further and further to the left on the number line every time, and we end up at negative 15. And sure enough, positive times negative results in a negative. Another way to look at this, rather than using repeated addition, is just by looking at a pattern. If we were to look at 5 times 2, that would be 10. And let's lower the number of 5s that we have then. Let's say 5 times 1. Okay, well, that would be 5. And if we had 5 times 0, that would be 0. And then 5 times negative 1. Well, even if I wasn't sure what that was going to be, I could just kind of look at the pattern here. It went from 10 down to 5. It got lower by 5 to 0. This will have to get lower by 5 to negative 5. And so here's an example of a positive times a negative is a negative. And so repeated addition is a great way to show that. And this pattern right here is a good way too. There's still one that we haven't talked about yet, though, and that's a negative times a negative is a positive. This is a little tougher. Repeated addition is not going to work here. We will look at a pattern, but before we do that, one thing I want to do is we talked about negatives as being opposites. What I mean by that is negative 3 is the opposite of 3. And if we were going to multiply two negative numbers together, we might have negative 4 times negative 5. Now, you wouldn't really do this when you were multiplying these numbers together. This is strictly just a way of looking at the fact that why is a negative times a negative a positive anyway? So I've got negative 4 times negative 5, and if I wanted to peel those negative signs off, so this is the opposite of 4 and the opposite of 5. Okay, so if I take those negatives and I put them out front, opposite of multiplied by the opposite of multiplied by 4 multiplied by 5. So essentially I just looked at these things one piece at a time. And now what I have over here is I have the opposite of the opposite. Well, if I take the opposite of the opposite, those two just cancel each other out and become positive. And now I have negative 4 times negative 5 becomes 4 times 5, which is just positive 20. That's probably my least favorite way to explain why a negative times a negative is a positive, but it's not good. It's not terrible. It's not awful. The opposite of the opposite. It's like turning a light switch on and back off again. They cancel each other out. Okay, another way to look at negative times negative is a pattern. We looked at a pattern a minute ago. And here, if we do, let's say, 2 times negative 3, and 1 times negative 3, and 0 times negative 3, and then negative 1 times negative 3. Let's see what happens with our pattern here. Because essentially we're just going All right, so I have 2 of these, 1 of these, none of these, -1. Okay, let's see what happens with the pattern. So if I had 2 times -3, well, just a minute ago, we got ourselves comfortable with the idea that positive times negative would be negative. So this will be -6. And then 1 times -3, then that's positive times negative. So it's going to be a -3. 0 times anything is just 0. And now if I look at the pattern that emerges here, I went from 2, 1, 0, -1. And over here, I went -6. It got bigger by 3. It got bigger by 3. It's going to get bigger by 3 again. -1 times -3 must be +3. Following this pattern, negative times negative is a positive. I like that very much. I think the pattern's good on both, actually. Finally, there's one other way I want to look at multiplying positive and negative with you. It's a little more visual. You might like it, you might not. It's okay either way. And forgive my artwork because I'm sure it's terrible. If we have a water tower, so I have this water tower, and the water level inside is right here. So there's my water level inside my water tower. And I find out that this water tower is leaking. So the water tower is leaking. And when that happens, the water level inside is going to go down. All right, you're thinking, what does this have to do with negative, negative, and positive? Here's what it is. The water level going down, that is a negative. Oh, my pen got disconnected. Hang on a second, it'll come back. There we go. This water tower, the water level inside going down, that's a negative. So the fact that it's leaking and the water level going down, that's a negative. So then if I go back in time, so if I go back in time, that would be a negative. And if my water tower is leaking, going down, but I go back in time, now this negative and this negative combine to make my water level go back up. Then that's positive. You might love all 3 of these. You might like one and not the others. However you want to explain this, I think if a kid were to ask, negative times negative is a positive, why? That would be a difficult question to answer. So having either just using the opposite concept or using this pattern or using, and you could come up with something that you might like better than this, but the idea the water level is going down, that's negative. We go back in time, now that negative and back in time negative together make the water level go up, and that's a positive. Any of those that you can use or something similar to help kids make sense of it is a great way to go. All right, a little more concrete than those. Scientific notation. You may be comfortable with scientific notation. You may have done a lot of work with it already, but it's a shorthand way to write really big or really small numbers. And when we write scientific notation, there's a key involved in that, is that the decimal point goes in after the first non-zero number. And that's as you read the number from left to right. Just to sort of clarify that, because it's a little bit strange. We don't talk about non-zero numbers very often. But if we had a number like 3,000, well, let me do 32,346. If we were going to put that number in scientific notation, we find the first non-zero number left to right and drop the decimal in right there. We'll finish off writing scientific notation in a minute, but that's where the decimal would go. And if I had a number that's on the other side of the decimal point, like we start out with 0.00325. If I was going to put that number in scientific notation, to figure out where the decimal goes, I go left to right, and I find the first non-zero number. So as I go left to right, well, that's a zero. No, that's a zero. That's a zero. Ah, there it is. There's my first non-zero number. The decimal goes after that. So that's how I'm going to figure out where my decimal point goes. Now let's talk about how to write a couple numbers in scientific notation. Let me get rid of these scribbles here first. So if we want to put a number in scientific notation, and let's say we have the number 273. 273 is not the type of number we would really use scientific notation for, but just to get the hang of it, we're going to use a little number like that. So, all right, if I want to put this in scientific notation, I'm going to go left to right and find the first non-zero number, that's the 2, and the decimal is going to go right here. So I'm going to rewrite this as 2.73. And then the scientific notation part is I use powers of 10. So what I'm going to write is 2.73 times 10 raised to some power. What I want to do here is I want to write an exponent on that 10 that when I do it, the number I end up with here, this thing that I express this way, has the same value that I started with, that 273. So I've got 2.73 times 10 to the, and so we don't have to do this every time, but at least when we're first starting out, let's see. To turn 2.73 into 273, well, let's see, the decimal point would move 2 places. And so my exponent's going to be a 2 because that's the number of places I'm moving the decimal. The decimal would move 2 places, so it's 10 to the second power. And then there's one other question you have to ask yourself. And there's memorization tools you can use, but honestly, and you can use those if you're comfortable with them. I think of it from, does 2.73 have to get bigger or smaller to turn into this number? It has to get bigger. So I want a positive exponent over here. Because 2.73 would have to get bigger to become 273, I want a positive exponent. And to rewrite 273 in scientific notation, it would look just like that. What we're saying is 2.73 times 10 to the second power has the same value as 273. If you're thinking, what's the value of that? I could just write 273. Totally fair. Typically, scientific notation is going to be used with really large or really small numbers. I just wanted to use a really simple one for our example. Let's look at another one. If we wanted the number 0.00517 to be written in scientific notation. Okay, scientific notation means I'm going to go left to right. I'm going to put the decimal in after the first non-zero number. The first number that's not a 0, that's where the decimal goes. That's going to be here after that 5. So when I rewrite this in scientific notation, it's going to be 5.17 times 10 raised to some power. That power is how many places did the decimal move? And it moved 1, 2, 3 places. So it's going to be 10 to the third. The only thing left for me to decide is that 3 going to be positive or negative? Like I said, there are ways to memorize this. If the decimal moves to the left, it's positive. If the decimal moves to the right, it's negative. And that's okay if you're comfortable with that. I tend to prefer to just think of it more of a number sense thing. I've got this number 5.17. What I meant for it to be was 0.00517. So this 5.17 would have to get smaller to become 0.00517. And since it has to become smaller, then the exponent will need to be a negative exponent. And so 5.17 times 10 to the negative third would give me 0.00517. Do you have any questions about that? I'm going to have you try a couple, but if you have any questions about this, writing a number in scientific notation, I want you to let me know. All right, let's try a couple, see how they go. My guess is just something you've probably seen before, but if not, and you have questions, don't be shy. Let's take a look. I'll set up a poll for this. Rewrite 413 million using scientific notation. This is a case where scientific notation would be valuable. Whoops. Okay. And that caret symbol is used to indicate an exponent. And so we've written 4.13, excuse me, shoot, 413 million in scientific notation. We'll go another 15 seconds and then talk about it. All right, let's see where we are. Okay, not unanimous, but strong agreement. That's good. That's a good indicator. All right. So let's take a look at this. Keeping in mind that when we use scientific notation, the decimal is going to go after the first non-zero number. So it's going to go after the 4. So we're going to have 4.13. The decimal always goes after the first non-zero number. Times 10 raised to some power, and that power is how many places did the decimal move? And that decimal here would have moved from where it was 1, 2, 3, 4, 5, 6, 7, 8 spaces. So it's going to be 4.13 times 10 to the 8th. And then the only thing to decide is whether this is a positive 8 or a negative 8. 4.13 would have to get bigger to become 413 million. So we want a positive exponent. So we're good right here at 4.13 times 10 to the 8th. While it's true that 413 times 10 to the 6th would have this value, it's not in scientific notation because scientific notation always puts the decimal after the first non-zero number. Let's try one more. Write the following using scientific notation. 0.00003141. I'll make a poll for this and give you a chance. We'll go another 15 seconds and then talk about this one. Let's see where we are. Okay. Very strong agreement, not unanimous. Let's talk it over. For this one, let's see. I'm putting it in scientific notation. So my decimal is going to go after the first non-zero number. So it's going to move to here after that 3. We keep the whole number. Couple that we did a few examples where they were only 2 decimals long, but we keep everything. So it's going to be 3.141 times 10 raised to some power. And the power will keep, well, let's see, how far did the decimal move? It moved 1, 2, 3, 4, 5 places. And then we just have to decide whether that's going to be positive or negative. Well, 3.141 would have to get a lot smaller to be 0.00003141. So we need a negative exponent on there. And so in scientific notation, it'll be 3.141 times 10 to the negative 5th. Any questions about scientific notation? Polls went really well, so I'm thrilled with that. But if you have questions, don't hesitate to ask them. Okay. Here's one I just want you to try. It involves remainders with decimals. I want you to be patient and careful as you come up with your answer here. A half-gallon container of juice contains 64 ounces. How many 6-ounce glasses can be filled from this container? And then the second part, how many ounces of juice are left over? I'm going to make a poll for this and let you try it. In the poll, it's just going to ask you how many ounces of juice are left over. I'm pretty confident in how many glasses can be filled. So the poll is just going to be how many ounces of juice are left over. We'll go another 20 seconds and then talk about this. Oh, so we're spread around pretty good on this. This turned out to be more challenging than I expected. All right, so let's talk through this one then very carefully. So we've got 64 ounces. How many 6-ounce glasses can be filled? So, this one's pretty straightforward as far as that goes. We're just going to do 64 divided by 6. The answer we get is 10.66666, and that repeats. And so how many 6-ounce glasses can be filled? Well, 10 can. That part I didn't expect you to have much trouble with. But then the second part of this, how many ounces of juice are left over? The dangerous thing to do here is to just look at that and say, well, my remainder is 6, so 6 ounces of juice. Well, wait a minute. Let's think about this for a minute. If we were to actually have our 64-ounce container and fill 10 glasses, how many ounces would that use? How many ounces are left? What we've got here is we're not looking at a base 10 system. We're actually kind of looking at a base 6 system. Without getting that deep into it, that's kind of what's going on here. So when I fill my 10 glasses of juice that are all 6 ounces each, so 6 ounces times 10 glasses, I've used 60 ounces. I started with 64, I've used 60, so I have 4 ounces left over. Hopefully that seems a lot simpler now than it did at first glance. It is very similar to converting a number to base 6, but you don't have to think of it in those terms for a problem like this. You can really just be sort of practical in your approach to this. I can make 10 glasses. Once I've filled 10 glasses, that's 60 ounces. And if I started with 64 and I've used 60, I have 4 left. Another type of problem solving reads like it would be a lot more complicated than it really is. A boat travels upstream at 8 miles per hour and downstream at 4 miles per hour. Now, what's important to recognize about this is we've got this stream, and in that stream, there is a current pushing one way or the other. That's why the boat can go, I got it backwards. My numbers are backwards here. Let me fix it. It goes upstream at 4 and downstream at 8. I'm sorry about that. Downstream at 8, upstream at 4. Downstream is with the current. So the current is helping push it down the river. And upstream, it's going against the current. So the current is actually slowing the boat down when it goes upstream. And there are 2 questions here. What is the speed of the current? And what is the speed of the boat if there weren't any current at all? If it was just in water that was still? There's a couple of different ways you can go about this. The first way involves setting up 2 different equations with 2 variables. And that's what we're going to do first. It actually kind of sets us up for the first question in our final quiz review. So what I know here then, when this boat's going downstream, it's going with the current. So I could say the speed of the boat plus the speed of the current is 8 miles per hour. And then when this boat is going upstream against the current, it goes 4 miles per hour. So the speed of the boat minus the speed of the current, because it's slowing it down. It's subtracting from the speed of the boat, would be 4 miles per hour. And now I have 2 equations and 2 variables. This goes all the way back to pigs and chickens at the very beginning of the semester. We can rewrite this in terms of one of them. The one at the bottom, I think I would do, if we add c to both sides, then we find out that b is equal to 4 plus c. And now I'm going to substitute. I'm going to take, because b and 4 plus c are equal, they're the same. I'm going to take 4 plus c, and I'm going to use that where the b was, and rewrite my top equation. When I rewrite that top equation, putting 4 plus c where the b goes, I get 4 plus c in for the b, plus c is equal to 8. Or 4 plus c makes 2c is equal to 8. And now I just need to solve that equation. Just a little reminder of solving equations. I'm trying to get c by itself. So I need the term with c by itself. So I need to peel this onion from the outside. So the first thing we're going to get rid of is that 4. What do I need to do to both sides to get rid of that 4? Very good. Perfect. Leslie, Emily, Nicole, awesome. Subtract 4. I'll subtract 4 on the left. I'll subtract 4 on the right. And then these will cancel, giving me 2c equals 8 minus 4 is 4. And then you guys are probably way ahead of me. The next thing we'll need to do here is divide by 2 on both sides. And when we do that, those 2's cancel, leaving c is equal to 2. First question here is, what was the speed of the current? I just found that. Speed of the current is 2 miles per hour. And then what is the speed of the boat with no current? Well, now that I know the current is 2, I could go back into either of these equations and find out the speed of the boat. I can plug in 2 for c and find out the speed of the boat. Anytime I can avoid negatives, I'm going to avoid negatives. So the equation I'm going to pick to use over here is that one. And if I know b plus c is equal to 8, now I know c is 2. So that's b plus 2 is equal to 8. Oops. Subtract 2 from both sides and find out that b is 6. So we just found out that the speed of the boat was 6 and the speed of the current was 2. To be 100% honest, a question like this can be done without all of that algebra. Now, I wanted to do the algebra because we're going to work on pigs and chickens here in just a minute. But you could look at this and say, well, upstream is 4, downstream is 8. So if there were no current at all, the boat would be right smack in the middle of those. With no current at all, it would be halfway between 4 and 8. It would be 6. So the speed of the boat with no current is 6. And then with the current, it's 8. So the current must be 2. You could absolutely do it that way. That would be just fine. Any questions about that one before we look at one more thing from section 4.4? Okay, just a little review of simplifying some problems involving integers. This is mostly about positive and negative numbers, but if we have negative 14 plus 36 divided by negative 11, first thing I want to remind you is this division bar here goes last. Simplify everything on top, simplify everything on the bottom, and divide last. And so here, if we have negative 14 plus 36, that would be 22 divided by 11 would give us 2. The kicker there is, oh, how about I do it right? 22 divided by negative 11. And now we have positive divided by negative. Positive and negative make negative 2. That's better. Let me know if you have questions about anything we do on this page. I have one more to look at with you, and that is negative 5 minus 9 divided by negative 7. Here again, we're working with positives and negatives. We've got to be careful. Negative 5 and negative 9. Many of you are probably perfectly fine going straight to negative 14 for that, and if you are, that's great. If you want to picture it on a number line, we go negative 5, and that puts me here. And then I go negative 9 from there, and okay, I land at negative 14. Nothing wrong with the number line. It's really useful for problems like that. And we're supposed to divide by a negative 7. Negative divided by a negative, just like multiplication. If I have negative and negative, I end up with a positive, and 14 divided by 7 would be 2. Let me know if you have any questions about that. Great question, Leslie. Let me look at that for a minute with you. So here, negative 5 minus 9. So we've got negative 5 minus 9. And remember, subtraction is the same as adding the opposite. So really, what this is, subtraction is the same as adding the opposite. So this is -5 plus -9. And so subtraction is the same as adding the opposite. So if it's easier to think of it as an addition problem, that's perfectly fine. Just make sure when you change it to addition, you use the opposite of the number you were given. Perfect. Excellent. Very good. Very good. And an excellent question also. Okay. Only other thing I want to say about section 4.4 is number 29 in the book includes some modeling review. So you may have to write an equation there, but I don't think you'll have any trouble with it. All right. Any other questions from 4.4 before we talk about that final quiz? All right, very good. If you think of anything you do want to ask, you absolutely can. As we go through this review for the final quiz, it'll feel a lot like a review for an exam. There aren't many polls. I'm just going to talk through some problems with you. It's material that goes all the way back to the beginning of the semester. Kind of nice, not only to review for this final quiz, but it's also a little bit of what you'll see on Tuesday when we do a review for the exam. I'm just going to go ahead and dive in. Feel free to ask questions if you have them. Some of this will feel like, oh, yeah, I remember that. Some of it will be like, boy, that feels like a long time ago. Maybe some of each. Anyway, here goes. A farmer looks out into the yard and sees pigs and chickens. He counts 24 heads and 80 feet. How many pigs are there? How many chickens? This is going to be very much like what we just did with the boat and the current. We're going to set up two equations, have two variables, and then we'll solve. So here, we're going to make one equation about the heads and then another equation about the feet. The equation about the heads, well, I have pigs and I have chickens. They each only have one head. So the number of pigs plus the number of chickens is going to be 24 because they each have one head. And 80 feet, so writing this about feet, pigs have 4 feet. So 4 times the number of pigs. Chickens have 2 feet. 2 times the number of chickens. I'm adding up all their feet, and I get 80. So I have my two equations and two unknowns, so I'm going to be able to solve this. What we're going to do then is we're going to use substitution, and I'm going to look at the simplest possible one, and that's right here. I'm going to rewrite that, and it doesn't matter which variable you get by itself. I'm going to go ahead and take that one and just, let's see, I'll rewrite it down here at the bottom, and I'm going to have p plus c is 24, and I'm going to subtract p from both sides. I'm going to subtract p over here and subtract p over here. Those are going to cancel, and now what I can see is that c is 24 minus p. So in this original equation where I used to have a c, I'm going to rewrite that, and I'm going to use 24 minus p where the c used to be. So we'll have p plus 24 minus p is equal to, oh, I'm sorry. I already did that part. I apologize. We're going to take 24 minus p and put it in for the c in the other equation. My goodness, I'm sorry. So we're going to put it in for c in the other equation. And we're going to have 4 times p plus 2 times 24 minus p, and that's going to equal 80. What we've done here is we said, all right, well, if c and 24 minus p are the same as each other, then wherever I have a c, I could put 24 minus p in there for it. And that's what we've done. Now I have one equation with one variable, so we can solve this and find out p. The way we're going to do that is first, we're going to use the distributive property to multiply through those parentheses. And we'll have 4p plus 2 times 24. Let's see, 2 times negative p, and that's going to equal 80. I have like terms here. I can combine this 4p and this negative 2p over here. So 2p plus 48 is equal to 80. And now, just like we did before with the b and the c, we're going to subtract 48 from both sides. And then on the left-hand side, those 48s will cancel. 2p is whatever 80 minus 48 is, 32. And then finally, we'll divide both sides by 2 to get p is equal to 16. One of the questions I was given is how many pigs are there? That's 16. And then once we know there are 16 pigs, we can go back into this original equation that was relatively simple. We know there are 16 pigs plus the chickens has to equal 24. You could subtract 16 from both sides, or you could just go, well, then there must be 8 chickens, and that would be correct. How many chickens? 8. Typically on the quizzes and exams where we worked on questions like this, it asked you for one or the other, pigs or chickens. Make sure you give the answer that it asks for. Let me know if you have questions as we go through any of these review problems. Arithmetic sequences. Those are ones where we have a common difference. It goes up by the same amount every time between the terms. We had some problems where we had to write the formula for the nth term, and those are really good questions. But here, this just says, find the 5th term of the following sequence. So first we have to go, all right, what is this? It went up by 7, it went up by 7. So it's going to go up by 7 every time. So I'll add 7 and have 25. I'll add 7 more and have 32. And that's the 1, 2, 3, 4. That's the 5th term. That's it. It's an arithmetic sequence because it went up by the same amount each time. And here we were just asked to find the 5th term. This term, or this sequence, is a geometric sequence. And in this one, instead of going up by the same amount each time, we either multiply or divide by the same amount to get to the next term. So here, let's see, 6 became 18. That's multiplied by 3. 18 became 54. That's multiplied by 3. So that's how we recognize geometric sequence. I'm multiplying by 3 every time to get to the next term. This also said find the 5th term, so we'll do that. I'm going to have to multiply by 3 again to get to the next term. 54 times 3 is 162. And I'd have to multiply by 3 again to get to the next term. And that's 486. It said find the 5th term. That's 1, 2, 3, 4. There's the 5th term, 486. Let me know if you have questions on those sequences. Arithmetic sequences can either go up by the same amount between the terms or down between the same amount between each terms. It's either addition or subtraction. Geometric sequences are either multiplication or division, is how you change from term to term. Okay. Some set theory. Intersection, union, and complement. Just a little reminder here. This would be our universal set. That's all the elements that are under consideration. Everything we are even considering. And then we have these sets A, B, and C that we've been given. And what we've been asked for down there is C complement union B. Just a reminder of the symbols. This goes back a ways. Intersection is that symbol. It's where they overlap. It's the elements that are in both sets. Union is that symbol, and that's when we join things together. And complement, we use an apostrophe to denote complement. The complement is the trickiest of these three. Complement is everything that's inside the universal set, but outside of the set we're talking about. So here in this problem, we're asked for C complement union B. So what we're going to do is we're going to find C complement, we're going to find B, and we're going to join them together. First, let's find C complement. C complement is going to be everything that's inside this universal set that's outside of set C. All right, well, C is 2, 6, and 8. So 2, 6, and 8. So C complement then is going to be 0, 4, 10. It's everything that's outside of C, but inside the universal set. Now, what I'm looking for this problem is C complement union B. So I have C complement over here, I have B over here. I want to join those two sets together. And when we join those together, let's see, it looks like 0, 4, 6, 8, 10. We want to make sure we include everything. We want to keep the 0, keep the 4, keep the 6, keep the 8. 10 happens to be in both. That's fine. We only write it once, but we want to make sure we include that too. We'll do another practice with sets like this. Please let me know if you have questions. I know, this can feel like a long time ago. This was September, so it's a little while back. Intersection, union, and complement again. We have those same sets. This time we want A intersect C complement. The parentheses mean something. Parentheses, just like with order of operations, mean do that first. So the first thing we're going to do here is find A intersect C, and then after we have A intersect C, we're going to take the complement of whatever it is we have. So first we'll find A intersect C. Intersect is where they overlap, what they have in common. So I'm looking at set A, I'm looking at set C. I want to know what they have in common. That looks like the 2 and the 6 and the 8. So that's the 2, the 6, and the 8 is where A and C overlap, intersect. It's what they have in common. Not done yet though, because this question said, find A intersect C complement. Be careful, look for those apostrophes when you're inside the quiz. So we want the complement of this set, which is everything that's inside the universal set, but outside of this. So A intersect C complement is going to be, well, let's see, 2, 6, and 8. Throw out 2, throw out 6, throw out 8. That's going to be 0, 4, and 10. So there's A intersect C complement. Back when we were doing Venn diagrams, I think these went really well. When we got in, or excuse me, we were doing set theory. These went really well. When we got into Venn diagrams, things got a little more complicated. But when we were doing the intersection, union, and complement questions, as a class, you did really well with those. More recent than this, adding in other bases. If we wanted to take 4, 7 base 8 and add it to 5, 5 base 8, we're going to use a process very much like we would use in our standard algorithm. We just have to remember that we're working in base 8. So if I have 4, 7, and I want to add that to 5, 5, working in base 8. If I just did 7 plus 5, that would be 12. Problem is, I can't have 12 down there. What I'm going to do then, because it's base 8, is I'm going to reduce this number by 8 and carry 1 8 over to the 8s column. Just a little refresher here. When we're in base 8, we have a 1s column, an 8s column. If we had another one, it would be a 64s column. And that's because base 8 means 8 to the 0 power, 8 to the first power, 8 to the second power, and so on. So what we're doing here is this. We add 7 and 5 and get 12. And because we're going to carry over an 8, we reduce this by 8. Make it a 4. That's a number that we can write there because base 8 only uses 0 to 7. So we can take 8 away from that 12. And what we're doing is we're carrying 8 over to here. We just write 1 because it's in the 8s column, so it means 8. I'll keep going. Might be more explanation than you need. 1 plus 4 is 5, and 5, that would be 10. But I can't have a 10 written there. So what I'm going to do is I'm going to reduce that by 8 and carry 1 over to the next column. That can come down as a 1, and then I end up with 1, 2, 4 base 8 as my answer. The key here is when we carry 8 because we're working in base 8. Let me know if you have questions about anything we're working on. Next, we'll do a subtraction. Here we have 311 base 6 minus 124 base 6. We're going to subtract this the same way we would subtract if we were using our normal base 10 and standard algorithm. I'm going to go to the ones column and I'm going to do 1 minus 4. The problem is I can't do 1 minus 4, so I'm going to have to borrow. I'm going to borrow over here from this column. That's going to go down. The key here is when I borrow, I'm not borrowing 10, I'm borrowing 6. So this becomes a 7. And then I'll do 7 minus 4, and that'll be 3. No problem there. Okay, now I want to do the next column. I do 0 minus 2. I can't do 0 minus 2. That won't work. So I'm going to have to borrow again. I'm going to borrow from here. I'm borrowing 6. So that goes up by 6. It went from 0 to 6 is why it turned into a 6. It doesn't just automatically turn into a 6. It's because we had 0. We had to increase it by 6, and that's why it's 6. And then I can subtract. 6 minus 2 will be 4. Go over to the other column. 2 minus 1. Hey, one I can do. And that's 143 base 6. This is also something that went really well. I may have mentioned it before. Typically, the final quiz goes really well. The concepts we're working on are big main ideas that we spend time on and tend to go well for students. And I hope that's true for you. I hope these feel, even if they feel a little bit like, wow, I didn't remember that, it's something that does feel a little bit comfortable. Please let me know if you have questions. A couple more to do. Even more recent, the discrete model. If that is equal to 1, show 1/3. And if you're jotting that down, it's a 3 by 5 array that we've got there. And the first thing we want to do is show 1/3. To show 1/3, what we want to do is we want to look for, well, let's see, I have 3 rows over here. So to identify 1/3, I just need to pick one of those rows, and that's 1/3 of the whole picture. If I want to show 3/5, I might go this way and say, well, wait a minute, there's only 3. That's not how I want to cut this up into fifths. If I want to try to cut this into fifths, I should be looking at the columns because there are 5 of those. And if I pick 3 of those 5 columns, I've identified 3/5 of the whole picture. Okay, here's one that presents something of a challenge. I haven't shaded it yet because there's a couple different ways I could go. But if we shade that in, and the question says, what fraction of the diagram is shaded? The most common mistake students make here is to go, well, there's 1, 2, 3, 4, 5 pieces. One of the 5 pieces is shaded, so it's 1/5. Don't do that. That would be true if all 5 pieces were the same size. They're not. These pieces down here are different size than the rest of them in the picture. So instead, what you want to think about, there's 2 different ways you could approach this. You could make every piece in the picture the same size. That would be perfectly fine. If you want to make every piece in this picture the same size as the one that's shaded, that works here. It doesn't work for every picture. But depending on the picture you're given, that could work where I'm going to cut these up and make them all the same size. Now, if they're all the same size, I can say there's 1, 2, 3, 4, 5, 6, 7, 8. One of them shaded, so it's 1/8. That works here in this picture. Some pictures might not be so agreeable with that. The way that I really want you to think about this is, how many of these would it take to fill up the whole shape? How many of these would it take to fill up the whole shape? And I've got one there, and okay, I'd have another one here, and then I would need 2 more here, and I would need 2 more here, and I would need 2 more here. That would make 8 altogether. Since it would take 8 of these to fill up the whole shape, 1/8 of this figure is shaded. As long as you don't look at that and say 1/5, I think you're probably okay. It'd only be 1/5 if they were all the same size, and since they're not, we have to adjust our thinking a little and think, how many of these would it take to fill up the whole shape? That's the fraction that's shaded. Gradually working our way to more and more recent, greatest common factor. If we want to find the greatest common factor of two numbers, we're going to find the prime factorization, and then we're going to keep whatever they have in common. It's a perfect example of intersection that we were just talking about with our set theory. So the prime factorization of 90. You might do it differently. That's okay. 3 times 30. 3 times 10. 2 times 5. You could break it down differently. Eventually, you'd get to the same place. And your prime factorization of 90 is going to be 2 times 3 squared times 5. Then we need the prime factorization of 105. Gosh, I don't know, but I know 5 will go in since it has that 5 on the end. So 105 divided by 5 is 21. That's 3 times 7. That's it. So this is just 3 times 5 times 7. I've got the prime factorization of each. Now, because I'm looking for the greatest common factor, I look for what they have in common. Where do they overlap? What do they both have? And as I look at these, that has a 3. This has 2 3s, but I can only keep one of them because they both have to have 2 3s in order for me to keep both of them. So I'm only keeping 1 3. All right. Hey, they both have a 5, so I can keep a 5. And let's see, no 2s over here, no 7s over here. So that's it. 3 times 5. The greatest common factor of 90 and 105 is 15. If you listed out all the factors of 90 and listed all the factors of 105, you'd see that the biggest one that they share is 15. Least common multiple, those same two numbers, 90 and 105. Again, we would find our prime factorization of 90 and our prime factorization of 105. Since we already have those, I'll just go back here and steal them. 2 times 3 squared times 5. And 3 times 5 times 7. When we're finding least common multiple, instead of looking for the overlap, we want to keep the highest power of everything. This is like union. We want to keep everything, and we want to keep the highest power of it. So, smallest number I have is a 2. We're going to keep that 2. I have 3 squared and 3. Well, I'm going to keep 3 squared then, because I'm keeping the highest power of every term. Okay, I've got a 5 over here and a 5 over here. I'm only keeping 1 5 because that's the highest power that either one of them has. And then I've got this 7. I got to keep that too. Now I need to multiply all this together. Let's see, that's 2 times 9 times 5 times 7. 2 times 9 times 5 times 7, 630. If I started listing out multiples of 90 and multiples of 105, the first one that I would get to that they would share would be 630. So that's the least common multiple, and that's how we find it, is by finding the prime factorization and then keeping the highest power of every term we see.